Today we're doing some fundamentals of the working with the mole. And the first step we need to do very often in a mole calculation is to find out the molar mass of a substance. So the question I ask here is, how do we calculate the molar mass of a substance? Answer: add the molar mass of the constituent elements multiplied by the number of times the element appears in the substance. So for example, what is the molar mass of butane, which is C4H10? You would multiply the mass of carbon, which is 12.011 grams per mole, times 4, and the molar mass of hydrogen, which is 1.00794 times 10. Add all that together, and get that the molar mass of butane is 58.1234. In another example, we use the formula mass. Because it's an ionic compound, it's not really proper to say molar mass because it's a crystal, but this is the unit that's repeated within an ionic compound. So it's more correct to say formula mass, but it's the same idea. The number of elements times the number of times the element appears in the substance multiplied by the molar mass of each substance. So 2 times the molar mass of lithium, 1 time the mass of carbon, 3 times the mass of oxygen gives you a total of 73.812 grams per mole for lithium carbonate. The next question is, how do we find the number of moles if we're given the mass? There's a very simple equation we can use for that, although I resist the use of equations because if you know the units, you can look at the units and find out what you're looking for. But for those of us who like to have that crutch, the number of moles, N, is equal to the mass of the substance divided by the molar mass of the substance. You'll see that the units of mass are in grams, the units of molar mass are in grams per mole. When you put them one over the other, the grams cancel, and the denominator of the denominator becomes a numerator, so the unit is moles. Here's an example. How many moles of butane is contained in a lighter with 10 grams of butane? Well, we just calculated the molar mass of butane at 58 grams per mole, so we're using this equation. We simply plug in the values. The mass is 10 grams. The molar mass is 58. 10 divided 58. Grams cancel. 0.172 moles. And we're not going to report it to that level of accuracy because the least accurate number we used in our calculation only had 3 numbers in it. So we're going to reduce ourselves to 3 significant figures. So we report our answer to 3 significant figures. If you do a prolonged calculation, you never round during the calculation. You would keep all the numbers in your calculator. You only round at the very end of the calculation. In another example, we have how many moles of lithium carbonate are contained in 1.05 grams. So again, we use the same formula. Number of moles equal the mass divided by the molar mass. The sample contains 1.05 grams divided by the molar mass, which we calculated over there for lithium carbonate. And we've obtained that it has 0.014 moles. And again, I reported the answer to the correct number of significant figures. When you report something to the correct number of significant figures, it often helps to set it in scientific notation. You'll notice that this is what I got in my calculator readout, but if I wanted to count significant figures, I wouldn't count the spacing zeros. So to see that more clearly, what I can say is simply take that decimal point and move it over 2 times. And if I do that, I put an exponent of -2 in the exponential form. And we'll see that it's 1.42 times 10 to the minus 2. If I was to move the decimal the other way, then it would increase the exponent to positive numbers. And here I've done an exercise to show how large the number 6.02 times 10 to the 23 is, Avogadro's number. It's 602 sextillion atoms. So by definition, in a 12-gram sample of carbon, you have 602 sextillion atoms. I wrote the number out here. Here's where the decimal place is. Now if I wanted to rewrite this whole big number as an exponential form, I would skip the decimal over 21 times, would bring me over here because it's 7 times 3 sets of zeros, and then 2 more times would mean I'd move the decimal place 23 times. So it becomes 6.02. There's where the decimal place is now, so I write 6.02 times 10 to the 23. That's 602 sextillion. Now it's much easier to write this than to write this very cumbersome number. Now, to give you an idea how big the number is, I said, suppose you had $602 sextillion and you spent $1 million per second. How long would the money last? This is a rate problem. Rate times time equals distance, where the distance is the amount of money that you have. the rate is the time, the amount of money you're spending per second. We want to solve for how long the money's going to last. That's the time. So I transpose the R, and we find out that time is equal to distance over rate. I enter the two values, 6.626 billion, the Avogadro number, divided by $1 million per second. The money would last this many seconds. And then I show you three conversion factors. 1 hour equals 3,600 seconds, 1 day equals 24 hours, 1 year equals 365 days. So let's convert that number of seconds into days. Works out to 19 billion years. It would take 19 billion years to spend a mole of dollars at a rate of $1 million per second.